Texas A&M University, professor of chemistry. His research interests involve solid-state chemistry and materials chemistry, and he's interested in designing and synthesizing materials with predictable properties and controllable properties, and I think we as catalyst chemists can appreciate that as a goal. Heterogeneous catalyst is obviously an area that he has an interest in, and we had him with us this morning and part of the afternoon discussing a couple topics that we were interested in. And as I mentioned in our meetings there, one of the things I really like about Abe Clearfield is the fact that he had about 10 years industrial experience, so he really understands the kind of problems we face as industrial chemists. So he's going to talk to us today on another topic, tin phosphonate chemistry as selective oxidation catalyst. So with that, Abe Clearfield.
Thanks, Mike. Well, I hate to disappoint you. Well, I am going to talk about tin phosphonates, but I'm also going to talk about zirconium phosphonates because, see, I've got a surfeit of these, because you need the background in order to understand the difference between tin. You would think that the tin phosphonates and the zirconium phosphonates, both being +4, are very similar. Well, there are similarities, but there's tremendous differences. And so I would like to just give you an introduction. With me, life begins with zirconium phosphate. Okay? So let me... So what I'm going to talk about is some background to metal phosphonates in general. Well, maybe I better use that one. Okay, so then phosphonates, sulfophosphonates, as Bronsted acids, and we did some acetone polymerization and esterification of salicylic acid, and then the tin phosphonates in the Baeyer-Villiger reaction. That's all very preliminary because we don't pretend that we're catalyst-type chemists. We make things. I have one person now who is trained in catalysis, and that's it. Okay? Okay, so I said life begins with zirconium phosphate because the structure is so similar to so many structures that we'll talk about. And what we see is it's a layered compound. Its formula is this, very simple. See, when I published the structure of this material back in '69, and so you have zirconium almost in a layer like that. The phosphate groups, 3 oxygens bond to 3 different zirconium atoms, and then the POH hangs into the inner layer space. So it's a solid acid. And you can intercalate amines into this, and you can exfoliate it, and you can do lots of things with this. Okay, so to make a phosphonate, you just substitute an organic group here, and you cook them up together, and you get something like that. So you get a phenylphosphonate. And so I did the crystal structure of that from powder because it's almost impossible to get a single crystal. Now, if you want to see the similarity to the zirconium phosphate I just talked about, if I hold it like that, this framework from the phosphorus over to the phosphorus on this side, it's exactly like zirconium phosphate, except that you notice that the phenyl rings are tilted at about 30 degrees to the layer. Okay? So that's why, I say you need to know something about the structure of zirconium phosphate to understand this stuff. Here are some of the little particles. It turns out, you see, this is 50 nanometers. These are about 50 nanometers on a side and very thin. This is the phenylphosphonate. It was one of the reasons that we had to work so hard to get a powder pattern, is we had to grow particles big enough, say 30 days at 200 degrees in a hydrothermal bond. But before we got something that we got such a good enough powder pattern to solve the structure. And then one of the things we did, and this shows some other things we can do, is the distance between these phosphorus is about 5.3 angstroms. So in other words, the phenyl groups are very tightly packed in there. So if we want to sulfonate this thing to get a Bronsted acid, we have to separate the groups. So for example, if we can put a hydroxyl group, that is, we have a mixed phenyl phosphoric acid, phenyl phosphonic acid. However, if you don't do it right, you won't get that. You'll just get zirconium phosphate on this side, and you'll get that on that side. So there are a lot of tricks in how to synthesize these things. But let's say we've done that, and now we've got this sulfonic acid down here, and it turns out, as we'll see in a moment, that it's a very strong Bronsted acid. Okay. So now, I can't take credit for this. This is our idealization of a structure where we have biphenyl and we have phosphonic acids on both sides, and we react it with zirconium. And so if each position is filled, you know, you've got a tightly packed, non-porous material. Now this is incorrect. In 1998, this I already did 20 years of work on it, but the first work was done by a fellow named Martin Dines when he worked for Exxon. And his idea, I saw his paper, and I met him at an ACS meeting, but he never would tell me what he was after, because what he was after, he said, eventually, because they made me a consultant, was to space these biphenyl rings and sulfonate them, or functionalize them so you can make a porous material that you can do chemistry inside the pores. All right? Well, it turned out that the reason that this says that I did this in '98, because that's when we started to really make porous materials. All right? Unfortunately, I have to say that Martin, we were at a Gordon conference together maybe 20 years ago or so, and he told me he wasn't feeling good, but he and his wife also had a career, and she was some kind of set up art shows, and so they were going to London, and she was going to set up this art show, and he was just going to relax. And when he got over there, he walked into the hotel and keeled over with a heart attack, and that was I don't know why things like that happen, but they do. So the idea is, if you could do this and actually make a space between them, and if you put 3 rings, then you can make it even higher this way, and if you could space it this way, so you say, okay, you're starting to think like a materials scientist, and you can shape these things. But it doesn't work that way. Nature doesn't let you work that way. It turns out that we can make porous materials by doing this kind of thing, but the pores are random. In other words, you can get small pores, big pores, all together. And so if you look at the isotherm, it looks like you have a huge spread of things. However, I just mentioned at lunch that my Jane Huang, who found a solution to how to make this stuff porous. It was very simple. She put twice the amount of zirconium in that stoichiometry would tell you. She heated it at a low temperature hydrothermally, like 80 degrees, and wouldn't you know, it comes out with 400 square meters per gram and regular pores. Now, ask yourself why. Well, the point is, we really don't know why yet. Okay, so let me show you, say, here is one of the samples that my current postdoc made. For example, this is, the isotherms we're doing here are at 10 to the minus 3 vacuum, but we've now doing them at 10 to the minus, starting at 10 to the minus 7 to access the smallest possible pores. And this is by the T-plot method, so I know we've gotten involved with lots of porous materials. We're doing lots of things. We're actually doing neutron scattering from these things. We're doing contrast matching and so forth and so on. So eventually, we will map out the pores in these materials, okay? So you can get pore structure from, we've gotten, or Jane, my Chinese student, who is now working for a catalysis company, was able to get, see here's 380 and the pore size has moved over. Here's another one about 14. This is where the peak is, as you can see. And so largely the pores are between 10 and 20, but I'm sure when we do DFT and we go down to lower, where we'll find out a lot more about these pores. And here is another trick we've used. We can change the character by using a methyl group here. This would be C patched to P. So we have to have a phosphonate group here so that it bonds to the layer in exactly the same way as the other ligand, right? But this one is easy to make because apparently what we're dealing with is hydrophobic, hydrophilic. So the OH is very hydrophilic, and the methyl is very hydrophobic, and so is the phenyl rings. So when we do this, so 440 square meters per gram, that's this one. And you can see some pores are sneaking over into the large region. 380, 17, that's this one. 314, that's this one. Okay? So you can say, okay, we can play with this. And when we sulfonate it, okay, then we have a very strong Bronsted acid. So, this is the young lady, Zhika as her real Chinese name. We call her Jane Wang. And she graduated last year. She got her PhD last year, and she's been working in industry. And Joy did all the electron diffraction work, all the microscopy for me. She was one of Canizzetti's students, postdoc for me. She's now teaching in Boston, okay? And this is the paper that we published in JACS. So we think it's going to lead to superacid, and I'll show you why we think so. Pore size dependent preparation of proton conducting nanopolymer membranes for use in fuel cells and catalytic membranes. That's where we're tending with this stuff. Because we can control the, so here's what the particles look like. These are the cross-linked. When we make it, they're micron-sized. 10 microns, 15 microns, and you can see the layering. You can see several micron thick layers that are glued together. If you think about it, you know, you have phosphonic acids on both sides. So on the surface, you also have a phosphonic acid sticking up like that, and if a zirconium or a layer comes near, it's going to grab onto it. See? So so when they grow irregularly, and you get big particles. But when we grind them up and look at them by TEM, it turns out here we found see, here's the length of the particle and here's the width, and so you can see the individual layers. There's about 9 layers here. See? And the interlayer distance about 14 angstroms, so you got 9 times 14. And you can just lay a ruler over there and you're within 5% of the correct value. Okay, now how do we know, well, what is this? Oh, what we're showing here is if we have the phenyl phosphonic acid and we sulfonate it, if I throw it in water, it exfoliates completely. It's just like you have a clear solution. But the particles are there because if we evaporate, we just come out, or we can cast them out and make a membrane. But the membrane doesn't hold together. I mean, if you put back in water, it's going to fall apart again. But nevertheless, if you're going to do catalysis, you can spread this out on a substrate, you see, and you're going to do this at elevated temperature and with no water, or even if you generate some water in the system, if you drive it off before it can exfoliate the material, you'll still have a catalyst. But, and the particles are very small, so we think that we're going to have high surface area here. But here's, for example, here's what happens when we sulfonate and we try to keep it dry. We see in the phenylphosphonic acid, the sulfonic acids push the layers apart and sit in between. And you see here we have two interlayer distances. Here we have, see this is the, before we sulfonate. Then we sulfonate, and then if we over-sulfonate, you see, we don't see anything here. We can put more than one sulfonic acid group into a phenyl ring, okay?
That's the distance between your zirconium layers of 14 and 20?
Yes. The first, see, you can see, this is the compound without sulfonation. And you can see we have a few reflections, but it dies out. We're only at 22 degrees and it dies out pretty quickly, all right? This is the phenylphosphonate, which we did work the structure out, okay? So then, you know, you have the two phenyl groups pointing at each other like that. So it's 14.8 angstroms, I think, in the interlayer distance. When we cross-link them, it's about 13.8 because now you've reduced it because you have no van der Waals space in between the rings. And there, you see, they don't exfoliate because you've cross-linked them all the way along the line. The particles are very stable. And so what I wanted to show you here is that the organic doesn't come out. You see, if we keep it dry, it doesn't start to decompose in a dry atmosphere until about 440 degrees. Well, this is TGA, so if we did it statically, it would be somewhat lower temperature, but you can see that they're fairly stable structures. Now here's how we show that it really is a strong acid. I don't know if the name Jim Hall means anything to you, but what Jim did is take zeolites, and he looked at acid scale, Bronsted acid scale of sulfuric acid, say 100% sulfuric acid, so it has what do you call it, the Hammond acidity number minus 12. And then you make 90% sulfuric acid, 80% sulfuric acid, and you measure the Hammond acidity function, okay? Now what you do, he worked with zeolites, and what he did is he took the 100% sulfuric acid, 90% sulfuric acid, and he allowed a little acetone in to it when he had the carbonyl carbon 98% carbon-13, so he could get a nice spectrum easily. And he looked at what happened. And then he did it with the zeolites. So then he was able to classify the zeolites on an acid scale relative to the sulfuric acid. And the way he did it is that when the acetone goes in, the Bronsted acid transfers a proton to acetone. And that causes a chemical shift. And so the amount of transfer is, or the acidity, is measured by the actual shift, the chemical shift for the carbon-13, carbonyl. Then, as it starts polymerizing, you see it dimerizes, right? Then it starts to form a circular compounds. That he can see all the shifts of the carbon-13, where it's going. It's very clever experiments. And he showed he was able to put zeolites on an acidity scale, all right? So if you had nothing but 100% sulfuric acid, the shift was here to 244, 100% sulfuric acid. And this is our material. This is our material at room temperature. Notice these little things are the polymerization of acetone beginning. We don't put very much in the gas phase, just a little dollop. Now later on we can put more in. And you can see at 353 K, you can see some more peaks starting to show up as the polymerization goes on. And here, if we just wait a while, we start to see the peaks coming up. So now we can pick off what these things are one by one. But you see that its shift was 243, almost as strong as 100% sulfuric acid. Okay? And so if we let so for example, we had a scale to work with where we would think we would see mesotyl oxide, isophorone, and so forth and so on, the C13 isotopic chemical shifts, where we would see them, okay? And so if we what happens to the peak that was at 243 is it starts moving down this way, because in the polymerization you create water, and so the water starts being picked up by the sulfonic acid, and so it's shifting back to less acid. So you really want to do this reaction so that you keep water away from the sulfonic acids. And I could give you a table, but I don't want to go into all of that, because but you can see that these are spinning side bands for these two peaks, but these are the polymerization products. And then if we warm it up, we can then see cracking, we can see olefins forming, and so forth and so on, okay? So you have to take my word for it about all of this. What I was talking about are these transactions always. So you see, for example, if you form mesotyl oxide, then you have 2 carbon 13s here. And then if you form phorone, you have 3 in this position. But then you start to form cyclic compounds, and you know where the carbon 13s go, and you see them in the spectrum. How we doing? Everybody doing fine?
Yep.
It's late, you know, people tend to sort of nod off and say, gosh, I can relax now, I don't have to think about anything. So, we did a little reaction here with both the sulfonated phenylphosphonic acid and the cross-linked phenylphosphonic acid, where we have pores. I'm not giving you any details on the characterization of the catalyst, because we'll be here for a long time, but I want to get to the tin phosphonates. But okay, this is a reaction, a esterification of salicylic acid using dimethyl carbonate by postdoc who did this reaction. This is one thing he did for his postdoc in India. And so he's very familiar with this reaction. He said it's very difficult to get it to go unless you have a really strong acid. And that's why he wanted to test it. So this is the reaction that he did. Okay. So it says, this reaction proceeds only in the presence of strong Bronsted acid catalysts like sulfuric acid at atmospheric pressure. In order to make it work with other Bronsted acids or weaker Bronsted acids, you have to do it under pressure. This is my postdoc, and you can see this is some of the work he did in India. And so the dimethyl carbonate has to be activated on a strong acid site for the reaction to occur. Solid acids like protonated zeolites catalyze this reaction under high pressure only. So we don't have any high pressure facilities in my lab for catalysis, so we just had to do it at 1 atmosphere with our catalyst. So it was very simple. Reactions were carried out in a round bottom flask under atmospheric pressure. So we added a little salicylic acid with dimethyl carbonate in a round bottom flask, and 0.03 grams of the sulfonated material was added, and then we heated to 135 for 4 hours. The reaction mixture was cooled, separated, and so forth. So As a test reaction, we did it with the non-sulfonated material. And then when we sulfonated, this has 2 phenyl groups on it. You know, we can put a phosphonic acid on almost anything and make these compounds. Sulfonated, 60%. This one is the cross-linked one that we got the highest reaction, highest conversion, and the highest also, it's 100% to the product you want. But so 65% conversion, 35% unreacted, and the product you want. And so this is some other things that he tried, and this is concentrated sulfuric acid, 58.2% under the same experimental conditions. So I think we really do have a strong Bronsted acid, and now we have to find what we're going to do that would be useful, that people will recognize as being a useful reaction that this stuff can do. Wow, so that's the background. Now we can get to tin phosphonates, okay? How we doing? Everybody alive, awake, listening?
Don't worry.
This is nice. See, I can see everybody's eyes. I teach a class of 60 students out there, and you know, the guys, we have very pretty girls at Texas A&M, if I must say so myself. Well, they like to sit up front. And the guys slink in the back, see, and slouch down so I can't see them. So I call on the guys and I say, you come up and sit over here today. I still don't get bad ratings. You know, at the end of the semester, they have to rate you. Okay. So, now, you saw these thin little platelets. The thin little platelets, before you sulfonate them, have only the surface area of the external surface, so it might be 10 square meters per gram, depending on the average size of the particles, no internal pores. Okay. So now, this Iapin came to me, this is another interesting tale, sometimes how luck, he was working for a startup company in catalysis. He worked for General Motors for 2 years as a postdoc. And he developed some catalysts for the automotive industry, but they farmed it out to a startup company instead of, you know, they didn't want to invest in it. I see what I see all over. They don't want to invest huge amounts of money in new processes. So he got a job, and he worked with them for a couple of years. He worked out a number of things for them, and then they folded. And he couldn't get a job in this market, so he was desperate, but he knew me. And so he had worked for Tony Cheatham at Santa Barbara, who was a good friend of mine. And I had visited there, and he knew me, so he kept calling me up, and I tried to get him. No, couldn't. I said, look, okay, I can offer you a postdoc. I'll try to get you a little more money than the average postdoc because you have children. You've been out in the field, you know, you've had a postdoc, you went 2 years at General Motors, and you've been out in the field. So he comes to work for me. And his PhD dissertation was on tin phosphates, okay? So he figured, oh, what the heck, why not make some phosphonates, tin? I thought they would be exactly identical to the zirconium. So what he comes to me is he says, guess what? He said, I don't know why he ran the surface area, but he did. He said he made the tin phenylphosphonate, which you saw was this layered compound with no pores in it, and it has a surface area of 300 square meters per gram. And I said, oh no, that can't be. And the composition is roughly this. So the zirconium, you know, except you have a tin here. So this, a comparable prep here was 8 square meters per gram. This is 300. Okay, so the pores were in the micropore region. And a mixed derivative with some methyl groups in there, he got as high as 500 square meters per gram. What's going on here? Here is one of the isotherms, for example. Almost type 1, you know, shoots right up and then over like that, almost like a zeolite. So we're saying, what does that mean? If we use the MP method of determining the pore size, now, because we go to a pressure of 10 to the minus 3, we're not accessing the pores down here. But now we have a balance where we can do that. So we're looking at, and we have software for density functional theory, so we're getting better idea of what's going on. I showed this so one of the things we're doing is neutron scattering, small angle scattering, because it can give you particle size, it can give you pore size, and if you do contrast matching, which means that you fill the pores with a scattering material that scatters like the framework, then what you do is blank out, you just see the particle. And then the scattering curve you get there and the scattering curve you got when the pores are empty, you can subtract one from the other and you can see the pores. So our first runs tell us that these are very small nanoparticles, okay? And I have, unfortunately, I forgot, the X-ray patterns, we're never going to get a structure. Here's some of the, this is the, just the methyl phosphonic acid with a few peaks, and here are the mixed derivatives and the phenyl. So this gives us the interlayer spec. So it looks exactly like there's zirconium, the X-ray patterns look exactly like there's zirconium phenylphosphonate. And now they're telling me they're nanoparticles, so what is going on here? So once I saw this SEM, it became clear, I think, what's happening. It forms, see, this is the scale, 200 nanometers, so you can see this is certainly micron size. The one behind it are certainly. But you see these little white things? Those are the particles. The particles are true nanoparticles. You don't have to work at it. You just have to make it. And you get these spheres. See? This is two fused together. Here's one. There's one behind it there. You know, if I showed you a picture and the magnification were much lower than this, you'd see a whole bunch of these little things like that. And we think the dark regions, maybe the dark regions are the compounds and the white regions are the pores, okay? But what I think is happening is the particles are so small and the number of layers that are stacked together are so small that you have high surface forces. And that the surface forces, how do you reduce the surface forces? What does a drop of water do? It forms a sphere, okay? So we think that that's what it's doing, and so that the pores are a house of cards type pores. They're not real internal pores. The particles are just too small. They're external pores. That's what's giving us this high surface area where, now, as part of the evidence now, we have put these things in and grown them at 30 days at 200 degrees. Say, we normally go to about 120 to 140 when we first made these things. And we can see the particles growing bigger and bigger. And surprisingly, what happens is the spheres get smaller and smaller. And the pores get bigger and bigger. So what we think is happening is that you're growing the particles bigger. And so if you have a house of cards and you have big particles, you're going to get big pores. See? But the pores are so small here that all the pores are in the micro region. So now I look at this and say, let's sulfonate it. Will it fall apart or will it hang together? But we also have made some where we cross-link. And there, now, what we can see is we start to form slabs, not spheres. Because in cross-linking, we're holding the layers together to a certain level. We think. You know, all of this is very new to us, okay? Again,
That's the methyl phenol?
Yes.
That's the methyl phenol, the mixed?
we can do both the methyl. Now, if we substitute methyl, we can go up to 50% and still get the spheres. When we go beyond 50%, they start to elongate, and finally, if we just do the methyl, it forms layered compounds of a rosette of layered compounds. So as we add more of the methyl group in, when we get beyond 50% methyl group, we start to see a new formation, and eventually, it's slowly going over to the rosette. So we have lots of evidence like that. Now we've made about 20 different kinds of compounds, and the cross-linked ones give us slabs, okay? Nanoparticles, but slab, very small particles, okay? So again, the stability is about like the others here. Usually with the pores, we pick up a little bit of solvent or water, and again, up here somewhere beyond 400 degrees, we start to see the organic dough. See, how are we doing on time? What time did we start? What time did we start?
We still have a lot of time.
Well, now I'm up to the Baeyer-Villiger reaction, see? To refresh your memory, because I didn't know this, I've forgotten a lot of my organic chemistry. The Baeyer-Villiger reaction involves transformation of ketones and aldehydes into esters and lactones, where hydrolysis turns the aromatic esters and lactones into phenols. So the phenols are the product you want. This reaction is important in organic chemistry as it provides a convenient route to substituted phenols. These phenols find uses in various fields such as agriculture, cosmetics, pharmaceuticals, and dyes, and useful as polymerization inhibitors and polyester stabilizers. And now some of them are employed in treatment of melanomas and inhibit the growth of tumors. So it's a good thing to shoot for if you can do something that they can't already do in industry. You know that the industry has lots of catalysts that are waiting in the wings. So it says the most common oxidants for the Baeyer-Villiger reaction have been per-acids, which have many disadvantages. They have a low oxygen content, are potentially explosive, may require strong acidity to increase the reactivity, and they produce byproducts. So we wanted to do it with hydrogen peroxide. We wanted to use hydrogen peroxide as the peroxide that we're going to use. Now, here's the interesting thing. I hope it's interesting. Korma published a paper in the Chemical European Journal in 2002 that he found that tin-4 embedded in a zeolite, in the framework of the zeolite, not in the ion exchange sites, in the framework, allows the use of hydrogen peroxide in place of per-acids. These authors state that the tin acts as a Lewis acid within the zeolite framework and is able to polarize the carbonyl group. The polarization increases the reactivity of the carbonyl towards hydrogen peroxide oxidation, so he's able to get some fairly good results. He's published 2 papers now by using hydrogen peroxide with beta, zeolite beta, with about 3% of tin replacing silicon in the framework, okay? So he published, he has a huge group. So when I said Korma et al., there are like 6 or 7 other names after it. And so we decided to do a fairly simple one, which he had done by using para-anisaldehyde, which the hydrogen peroxide will convert in this way, and then if you continue the reaction, hydrolyze it over to the phenol. So this is a simple reaction. 80 degrees in toluene, which is exactly what he did. In other words, Korma's group did 80 degrees in toluene. Again, we don't have any fancy setup, so we just set up 50 milliliter flask and holding a certain amount of anisaldehyde, para, mixed with small amount of peroxide and toluene as the solvent and so forth. 80 degrees in an oil bath for 4 hours, and then we took it out and analyzed the products. We did gravity filtration, just let it settle, and took off the solution and analyzed for what we got. And we used the GC, inserted in the GC, and we also did GC mass spec now. Now, don't get frightened, because I hate people who give lots of data on one slide, because you can never get through the slide before it takes it away. Well, as you see, up till now, I wasn't guilty of that. But I asked my postdoc to put the data on the slide, and this is what I got. All right? Not bad, not bad, all right? So, we used different phenylphosphonic acids, and here with the methyl, and we used HF in some of the reactions in order to solubilize the whole thing and get the reaction, that is to get the tin phosphonic acid in a shorter period of time. So these were the conditions that we made them. Now, I want you to look at the BET surface area, 259 for this one, 226 micropores, and here's the type of isotherm we got. But you can see as we go down, we see some of them get much higher surface areas with a type 1 isotherm and so forth and so on. We tried all of those to see what would happen. Because as you saw, the reactions don't take very long, 4 hours. I tell them, you can do 2 a day. Well, so it turns out, interestingly enough, that the conversion depends not on the total surface area, but the amount of surface area that was external. And so, almost a straight line here, as you see, here's the conversion percent, and here's the T method external surface area. So, for example, the last 2 samples there, which I didn't let you see, had surface areas of 140 and 120. That was not the internal pores, but the external surface. And of course, most of them had low external surface area and a lot of internal pores. But you see, we got the conversion. So what is happening here? We don't know. I'll give you some speculation. But look at the yield. I mean, the conversion we're getting on the first trial in simple, but we have a lot more tin than you've got in a zeolite, right? We have a tin holding every one of those phenyl groups. So what's doing the catalysis? Well, so here's now the selectivity. What this means is that the longer we allow it to react, the more the phenol we get, rather than the ester. Okay? In other words, we're hydrolyzing it to the phenol. Remember, we had an oxygen up here with an organic group up here, and then we hydrolyzed that off. So all that's happening is, if we let it cook long enough, then whatever the conversion is, that's what the selectivity will be. So we can just hydrolyze the organic off, which we haven't tried to do separately, and that's what we've set up. In other words, in separate reactions, they're hydrolyzing the results. Okay? And Korma used 3 solvents. He used the toluene, tertiary butyl methyl ether, and dioxane. And so we're making a comparison. So this was a 4-hour run, so we don't get 100% selectivity because we haven't hydrolyzed all of the material that was converted. So for example, we got in toluene, in this particular run, we got close to 45% in a short run. Did I say 4 hours? No, 14 hours it says, in this particular run. And we compared the same sample with terse-butyl methyl ether and dioxane. The conversions were about the same in terms of selectivity, but, you know, in percentage. But you see that the conversion was much lower in the other solvents. So it is solvent dependent. Well, we think if the solvent is able to swell the pores, because they're not connected, right? House of cards, you can swell them. Then maybe the reaction just going on around the edges of those little spheres. All it has to do is go in and come out. Now here is something interesting that he did. This is pure tin. This is, these are mixed derivatives with zirconium. And this is the ratio. 1 tin, 2 zirconiums. Okay? About the same conversion, about the same higher selectivity, percent selectivity. 1 to 5, about the same conversion, a little bit higher. And so what's happening here? We're diluting it. When we did it with zirconium, nothing happened. If we did it with zirconium phosphate, nothing happened. But here, if we combine the tin, and we have a 1 to 5 ratio, we have 5-fold zirconium over tin, we're even getting better results. And let me show you what the particles look like after the reaction is done. So this is now 100 nanometers magnification. So you see, these are the particles we started with. See the spheres and the little spaces between the particles? Okay? And here's what it looks like after we're done. And you see, this is also 100 nanometers, but notice that the bar is much smaller than it is here. So for example, this is a much bigger. And it looks like some of the spheres have fused together, and that we now have some fairly big openings here. Okay? So there is something happening to those little spheres during the reaction, that they come out differently, in different topology than when we started. So now we want to see what have we made as a result of the reaction. Korma gave a mechanism which the reason I'm showing you this is he had 2 mechanisms. One, this is for the anise aldehyde, and I took the organic off this end. But what he's saying is that the hydrogen peroxide attacks this position. This is the carbonyl position. And then it forms a complex. The peroxide forms a complex, which is called, I'd never heard of this. Oh, any of you hear Krigi reaction? Krigi complex? I never heard of it. Well, maybe he's better informed than I am. Then you have a shift of the phenyl ring over to the oxygen here. So this is what you get. That's what we wound up with. And then if you hydrolyze it off, and see, we haven't hydrolyzed it off with water. We just let it sit in there. So if we do the next step, we probably would get a selectivity of close to 100%. Okay, so actually, we got a better conversion than he did with the zeolite in a very simple reaction at atmospheric pressure and very simple conditions. So, and here he has another mechanism that he gave with other aldehydes and ketones. He shows a complex where the tin is in there. And here he shows no tin in there. So I have to pose a question to all you catalyst types. This is the suspenseful moment, see? You drink the water while everybody's saying, what's he going to say? our NMR shows that the tin is probably 8 coordinate. Because we have a number of 6 coordinate tin compounds, and we measure the NMR, and it's around 600 to 700 negative. And this stuff is always past 800. And that's in the regime where there are few 8 coordinate tin compounds we fished out of the literature. So if this tin is 8 coordinate, it's surrounded by oxygens. I don't think that this mild reaction is going to make the aldehyde or ketone touch the tin. So what's causing the reaction? Now, my postdoc thinks that we have defects in the structure and that it's contacting the tin in the defects. And I can't say that he's wrong, because it's very possible that the way we make the darn thing, that there are defects in it, okay? Because we don't have enough structural information now to say what we have, okay? So, so our comparison with tin beta as a zeolite conversion, see this one, I put an asterisk, I should have said something down here. The run was for 7 hours, not 4 hours. And our run here with the tin phenylphosphonate, and this particular run, which we tried to duplicate his work on the beta zeolite, we got a 72% conversion, 89% selectivity in 4 hours, and they did 7 hours, okay? So ours was a 4-hour run, his was a 7-hour run. Now, can anybody answer me this? Cormus said, and now what they're trying to do is to find out where the tin is in the beta lattice, so that they're probably finding out that it's not just the tin that's causing the reaction, but that it sits in a particularly reactive part of the framework, that is, accessing a pore, so that the tin can be complexed by the aldehyde. But unless we have defects in our compound, that there's something missing there and it can access it, if we know that, we can then tailor make the stuff so that we build in defects and get higher conversion rates. But this is just the beginning. We'd only done this with tin phenylphosphonate, except we did have some substitution of methyl. And the methyl derivative, when we put the methyl in, the yield fell off. The conversion fell off. But we have cross-linked materials, we have functional groups, we put carboxylases, amino acid groups on the organic end, and still the phosphonic acid makes these spheres. So I leave you with that thought. What have we wrought here? Is it going to be of any value to anybody, except publications for my students? So we've prepared non-pore pillared and pillared, and we can maintain the pores in this area. We can functionalize the aromatic rings. So I've only talked about sulfonic acids, but we can put all kinds of things on the organic part so that we have a whole family of these materials. So I leave you with that, and thank you for listening, and I'm thankful you all stayed awake. Okay? Questions?
The tin derivatives, have you measured the acidity like you did in the zirconiums, or?
Well, no, because we didn't sulfonate it, and there's no reason for us to thinking that these are Bronsted acids. See, if we did, when we did the zirconium phenylphosphonate, we didn't get a shift at all. I mean, there may be a few Lewis acid sites there. I mean, if we use pyridine and maybe sorbate on a few Lewis acid sites, we might find some. But we didn't sulfonate these things. All we did was just take the tin phenylphosphonate. My postdocs, I asked them, I said, what did you put there that makes the reaction go? He said, nothing. It's the tin that's doing it. And I said, I don't believe you. And so then he put the zirconium in, and made the mixed derivatives. You know, we can make a complete solid solution between tin and zirconium. And I said, no, wait a minute. The zirconium is 6 coordinate. We think the tin is 8 coordinate. What are you telling me? Well, what I'm telling you is that we have a lot of work to do to figure out what's going on. But I think we've really discovered a tremendously versatile and hopefully practical system of materials that we can work with that will do some really nice work in catalysis. So, okay? Any other questions? Yes?
Yeah, I have one. Is there any idea why, when you have the aryl aldehyde, the substitute benzaldehyde?
Yeah.
I mean, if you think of the Baeyer-Villiger reaction as, you know, an insertion of an oxygen as the net thing,
Yes.
do you have any idea why it inserts into the carbon-carbon bond and not the carbon-hydrogen bond to make a carboxylic acid? Because that's normally an easy oxidation to do, whereas...
Right. You would think that, right? You would think that you have an aldehyde, you put peroxide in, you make an acid. And if you do it under mild conditions like this is what happens. And if you ask me why, I don't know. I'd have to ask my organic colleagues something about, tell me about these Baeyer-Villiger reactions and what mechanisms do you have for this? You know, I mean, it's, industrially, these things are done on a large scale. So, but what Corman's discovery was that he can do it with a zeolite by putting the tin inside the zeolite. Now, I would have never guessed, if I were working with zeolites, I would have never guessed that tin would be the one that would do the job. So somewhere in the back of his brain, or one of his colleagues or students, thought of that, right? But they don't get the little star beside their name. He does. He has I mean, he's got a reputation such that people come from all over the world to work in his laboratory. So there's lots of good ideas that are floating around that he works on, okay? But I would have never, in my experience, I would have never guessed that you put tin in there and it's going to do this reaction, okay? So you can do, I mean, the advantage is you do it with hydrogen peroxide and not the per acids.
And in this industry, are the per acids normally used, right?
Yes. Yes, and you know, they have to be extremely careful for those things explode. I don't know about hydrogen peroxide. I imagine if you use a 30% solution, then it's fairly safe. If you use concentrated peroxide, you're in trouble. You could be in trouble. We're using about a 30 to 40% solution, somewhere in there. Buy it fresh. Okay?
How does this compare to sulfated zirconia
How does it compare?
and the acidity? How does it compare to sulfated zirconia? Is it more?
I don't know. we haven't tested that. We haven't tested for its acidity. As I said, the zirconium phenylphosphonate has a small amount of Lewis acidity, no Bronsted. If we sulfonate it, it becomes a very strong Bronsted acid. Now, since we can adjust the acidity by putting less acidic material than sulfonic acids in, right? We can put phenols in, we can put carboxylic acids in, we can put mixtures of these in. You know, if you know your organic chemistry, and by the way, I've forgotten most of my organic. I know enough to get by. But out of the blue, I got a letter from a guy in Poland. And he said, oh, I'm reading some of your papers. I'm very happy to read them because I spent better part of my career making phosphonic acids. Okay? So he says, how would you like me to make some for you? If you have some that you would like me to make, I'll make them for you. Well, that's like God sent me a present, and it wasn't even Christmas. So I said, sure, why don't you make this for me? And about a month later, he sent me a vial full of this stuff. So then I went and got a U.S.-Poland National Science Foundation grant so I could go and visit him and bring him over. And as a matter of fact, he's coming for a month to my lab on Sunday, this coming Sunday. So we already have 3 papers together, and now we know some ligands that we really want. And I hope he can teach my students how he does these. I mean, we've made the simple ones, but as you get more and more complicated and got more and more functional groups, the stuff gets a little tougher to make. But he can make them, so that's another plus that we have. You know, sometimes he sends things your way and sometimes he takes away, so. Okay, anything else? Yes.
You refer to the 10 NMR, is that what you were saying?
Yes.
About the 8 coordinate?
Yes.
And do you see any changes in all these transformations, say during or after the peroxide reaction?
Yeah, we haven't looked at the NMR yet. I have to push him we look at tin and phosphorus. We could look at carbon also.
But the 10 is where your evidence for the 8 coordinates
Yes.
is?
What we see, tin 119 isotope, we see, for example, in tin oxide is 6 coordinate, okay, and it is right on 600, negative 600, and we use that as a standard, okay, and it shifts 200 and some more negative, and so we looked at. If you look at the literature, then most of the tin compounds are 6 coordinate, fall in the like 550 to 700 or something, and the few 8 coordinate compounds we found are in the region we are. That's the only evidence we have that it's 8 coordinate, except we have gotten a synchrotron data set for the methyl compound, methylphosphonic acid. It's a very simple space group, and I try to tell my postdoc you should be able to see this structure in your head. But what happens